Look up at the night sky on a clear evening. Away from city lights, standing beneath the stars, you see something that has captivated humanity for thousands of years. Thousands of brilliant points scattered across infinite darkness. The Milky Way stretching overhead like a river of light. Ancient civilizations built entire religions around this view. Poets wrote sonnets. Scientists dedicated their lives to understanding it. But what if I told you that everything you see up there, that entire breathtaking panorama, represents almost nothing, not a small fraction, not even 1%, essentially zero? Let me show you exactly what I mean. When you stand beneath that perfect night sky with nothing but your eyes, no telescope, no binoculars, just naked human vision, you can see approximately 9,000 stars. That number changes slightly depending on where you are standing and how dark your sky is, but 9,000 is the absolute maximum for human eyesight under the most ideal conditions possible. 9,000 stars scattered across the entire dome of heaven above you. Now here comes the part that changes everything. The Milky Way galaxy, our home in the cosmos, contains somewhere between 100 billion and 400 billion stars. Even using the most conservative estimate, we are talking about 100 billion stars in our galaxy alone. You can see 9,000 of them. What you see with your own eyes represents roughly 200,000ths of 1% of our own galaxy. Read that again. Not 2%. Not even a fraction of 1%. 200,000ths. The most spectacular night sky you have ever witnessed shows you an almost unmeasurably tiny slice of just the Milky Way. Not the entire universe. Not even a meaningful sample of nearby space. Just our single galaxy. Every constellation you learned as a child. Every star you wished upon. Every meteor you watched streak across the summer sky. All of it combined represents a sample so microscopically small that it barely qualifies as a sample at all. You're looking at the cosmic equivalent of examining a single drop of ocean water and thinking you understand the Pacific. But the scale gets worse. Much worse. The observable universe spans approximately 93 billion light-years across. Notice that word carefully. Observable, not observed. Observable means theoretically detectable if we had perfect instruments and unlimited time. Observed means we actually pointed our telescopes there, collected the light, measured the data, and catalogued what we found. The difference between those two words represents almost everything that exists. Astronomers estimate there are roughly 2 trillion galaxies in the observable universe. 2 trillion separate island universes, each one containing anywhere from millions to trillions of stars. Some are massive spirals like our Milky Way. Others are dwarf galaxies barely holding themselves together. Some are elliptical giants that devoured dozens of smaller galaxies over billions of years. Each one is a cosmic city unto itself. When you multiply all those galaxies by all their stars, you get a number that breaks human comprehension. 200 billion trillion stars. That is the current estimate for the total number of stars in the observable universe. 200 billion trillion. There are more stars in the universe than grains of sand on every beach on Earth. More stars than seconds have passed since our planet formed 4.5 billion years ago. More stars than breaths taken by every human who has ever lived. And you can see 9,000 of them. This is not just a failure of human eyesight. This is something far more profound. The night sky is not showing you a representative sample of the universe. It is not even showing you a biased sample. It is showing you almost nothing at all. The darkness between the stars is not empty space. It is not a void waiting to be filled. That darkness is packed with galaxies, billions upon billions of them, so distant and so faint that their light never reaches your eyes with enough intensity to register. The blackness you see is not absence, it is limitation. Your limitation. The limitation of biology and distance, and the fundamental physics of light, travelling across expanding space. Every patch of seemingly empty sky contains galaxies. If you could see in infrared, if your eyes were 1,000,000 times more sensitive, If you could stare at one spot for days and collect every photon that arrived, that darkness would explode into light. In 1995, astronomers pointed the Hubble Space Telescope at a tiny region of blank sky near the Big Dipper. The area was so small you could cover it with a grain of sand held at arm's length. They kept the telescope pointed there for 10 days straight, gathering light. That tiny empty patch revealed 3,000 galaxies. 3,000 entire galaxies in a spot smaller than a sand grain seen from across the room. Extrapolate that across the whole sky. Multiply it by every apparently empty patch of darkness you see above you. The universe is not sparse. It is not mostly empty with occasional islands of matter scattered throughout. It is dense, packed with structure, overflowing with galaxies and stars, but separated by such enormous distances that light itself takes billions of years to cross the gulfs between them. Your perception of reality is catastrophically wrong. The mental model you build from looking up at the stars bears almost no resemblance to what actually exists out there. You think you see the universe when you see the Milky Way. You think you understand cosmic scale when you imagine billions of galaxies. You think you grasp infinity when you contemplate all those stars. You're seeing essentially nothing. Most of the universe remains invisible to you, not because it does not exist, not because it is hidden or forbidden, but because the distances are so vast, the light is so faint, and our instruments have only just begun to scratch the surface of what is really out there. We have built our entire understanding of cosmology, of galaxy formation, of star birth and death, of dark matter and dark energy, from studying that tiny visible fraction. From 9,000 visible stars and a few million catalogued galaxies out of 2 trillion, we constructed theories about the origin and fate of everything. We mapped the shape of space-time. We calculated the age of the universe. We predicted its ultimate destiny. What happens when we finally see the rest? What changes when the invisible becomes visible? How many of our theories will survive contact with the full reality we have been missing all along? That question should terrify and excite you in equal measure, because the universe we have not yet seen is not just more of the same. It is not simply additional copies of what we already know. The unseen universe is full of surprises, and we are about to discover just how little we actually know. So we have established something unsettling. The universe you think you know is almost entirely invisible to you. 9,000 stars out of hundreds of billions, a fraction so small it barely registers as existing at all. But now we need to talk about something even more troubling, something that should fundamentally shake your confidence in everything astronomy has taught you about the cosmos. Galaxies are the building blocks of the universe. They are not just collections of stars. They are vast, gravitationally bound systems containing stars, gas, dust, dark matter, and often supermassive black holes at their centers. Everything we understand about cosmic structure, about how the universe evolved from the Big Bang to today, depends on studying galaxies. They are the fundamental units of cosmic architecture. Current estimates place the total number of galaxies in the observable universe at approximately 2 trillion. 2 trillion separate cosmic cities, each one a complete world unto itself. Some contain only a few million stars. Others hold trillions. Some are actively forming new stars at ferocious rates. Others are dead. Their star formation shut down billions of years ago. Each galaxy has its own history, its own story of birth and evolution and perhaps eventual death. Now here is the devastating fact. As of 2025, astronomers have catalogued only 10 to 50 million galaxies in any meaningful detail. Let that number sink in for a moment. 10 to 50 million galaxies studied out of 2 trillion that exist. Even if we use the higher estimate of 50 million, we are talking about roughly 2.5% of all galaxies. For every single galaxy we have examined, studied, measured and catalogued, approximately 40,000 galaxies remain completely unseen. 40,000, not 4, not 40. 40,000 galaxies for everyone we know anything about. Imagine walking into a library containing 1 million books. You want to understand what knowledge that library contains, what stories it holds, what information is preserved within those pages. So you randomly select 25 books, read them cover to cover, and then claim you understand the entire library. That is essentially what we have done with galaxies. We have read 25 books and declared we understand a 1,000,000 book collection. But the situation is actually worse than that analogy suggests. Because the galaxies we have studied are not a random sample, they are heavily biased towards certain types. We study the galaxies we can see most easily. The bright ones, the large ones, the ones that emit strongly in wavelengths our telescopes are designed to detect. Faint galaxies, small galaxies, galaxies that emit most of their light in wavelengths we are not monitoring, these remain invisible to our surveys. Most galaxy counts do not come from direct observation at all. They come from statistical models. Astronomers observe a small patch of sky, count the galaxies they find there, measure their properties, and then extrapolate those numbers across the entire observable universe. This is not bad science. It is necessary science given our limitations. But it means our total galaxy count of 2 trillion is essentially an educated guess based on sampling an almost invisibly small fraction of space. Think about what this means for our understanding of cosmic structure. When astronomers talk about galaxy evolution, about how galaxies form and grow and merge over billions of years, they are building theories based on studying 2.5% of the available examples. Every model of galaxy formation, every simulation of cosmic structure, every theory about how galaxies interact and evolve rests on that microscopically tiny foundation. Would you trust a medical study that examined 2.5% of patients and then made sweeping claims about all of humanity? Would you accept an election poll that surveyed the same fraction of voters? Yet this is the data foundation supporting much of modern cosmology. The galaxies we have studied are not representative. Large spiral galaxies like the Milky Way dominate our catalogues because they are bright and easy to see. Elliptical galaxies, which are equally common, appear frequently in our surveys because they are often massive and luminous. But dwarf galaxies, which may actually be the most numerous type in the universe, are severely undercounted. They are small, faint, and difficult to detect unless they are relatively nearby. Some types of galaxies might exist that we have never seen at all. Galaxies that emit most of their light in infrared wavelengths we have not thoroughly surveyed. Galaxies hidden behind dust clouds that absorb their visible light. Galaxies so diffuse and spread out that our instruments cannot distinguish them from background noise. Entire categories of cosmic structure might be missing from our current understanding simply because we have not looked in the right way or in the right places. This is not hypothetical speculation. It keeps happening. Every time we build a more sensitive telescope, every time we survey a new wavelength of light, every time we look deeper or with better resolution, we find things we did not expect. Galaxies that formed earlier than our theories predicted. Structures larger than our models said were possible. Objects that should not exist according to our understanding of physics. The universe does not care what our theories predict. It simply exists, vast and complex and mostly unseen, waiting for us to catch up. Consider what this means for the search for life beyond Earth. If we have only examined 2.5% of all galaxies, then we have only surveyed that same microscopic fraction for potential habitable worlds. Every discussion about whether we are alone in the universe, every calculation of the odds of intelligent life existing elsewhere, depends on data drawn from an almost comically insufficient sample size. We are trying to answer one of humanity's deepest questions, whether we are alone in the cosmos, using information gathered from 2.5% of the available data. It is like trying to determine whether fish exist by examining a single cup of water from one random location in the Pacific Ocean. You might find plankton, you might find salt, you might find nothing but water, but whatever you find, you have learned almost nothing about the ocean itself. Our cosmic map is not incomplete. That word is far too gentle. Our cosmic map is barely started. We have sketched the rough outline of a few neighborhoods while claiming to understand an entire planet. We have counted a handful of buildings and extrapolated the architecture of a civilization. We have seen a fragment and declared it representative of the whole. And yet, from this absurdly limited dataset, We have built sophisticated theories about dark matter, dark energy, cosmic inflation, and the ultimate fate of the universe. We have calculated the age of the cosmos to within millions of years. We have mapped the large-scale structure of space-time itself. Either we are extraordinarily lucky that our tiny sample happens to be representative of the whole, or we are missing something fundamental. Which do you think is more likely? That the universe conveniently arranged itself so our limited observations capture its true nature, or that we are still blind to most of what exists, still ignorant of phenomena and structures and types of galaxies that will overturn everything we think we know? The answer should be obvious and deeply humbling. You might be wondering something right now, something that seems obvious. If we have only studied a tiny fraction of galaxies, if most of the universe remains unseen, why not just point our telescopes everywhere and observe it all? Why not scan the entire sky, catalogue every galaxy, and finally build a complete map of the cosmos? It sounds simple enough. We have powerful telescopes, we have sophisticated instruments, we have the technology. So why have we not done it? The answer reveals a problem so fundamental, so built into the nature of observation itself, that it changes everything you think about astronomy. This is not about money or time or willingness. This is about the brutal mathematical reality of trying to observe something as vast as the universe with instruments as limited as telescopes. Let me start with a number. The full sky, the complete sphere of space visible from Earth in all directions, covers approximately 41,000 square degrees. That is the total area we could theoretically observe if we pointed telescopes in every direction and captured every photon of light arriving from every corner of the cosmos. 41,000 square degrees. That is our complete observational canvas. Now consider how telescopes actually work. They do not scan the sky like your eyes scanning a room. They stare at tiny patches of space, often for hours or days at a time, collecting light photon by photon. The smaller and fainter the object you want to see, the longer you must stare at it. Distance makes things faint. Incredibly, impossibly faint. A distant galaxy might send only a handful of photons per second toward Earth. To detect it, to actually gather enough light to form an image and measure its properties, you need to point your telescope at that exact spot and wait. The Hubble Ultra Deep Field, one of the most famous astronomical images ever captured, shows this problem perfectly. That image covers a patch of sky so small it represents 113 millionth of the total sky. 113 millionth. You could fit that entire image inside the area covered by a grain of sand held at arm's length. It is almost invisibly tiny compared to the full sphere of observable space. To capture that single image, astronomers pointed Hubble at that one spot for hundreds of hours. They collected data over multiple observation sessions, carefully stacking exposures, filtering out noise, gathering every possible photon that arrived from that particular direction. The result was stunning. That tiny patch revealed thousands of galaxies, some so distant their light had travelled for over 13 billion years to reach us. It showed us galaxies that formed when the universe was less than 1 billion years old. But here is the crushing reality. If you wanted to observe the entire sky with the same depth and sensitivity as the ultra-deep field, if you wanted to see every faint distant galaxy across the complete 41,000 square degrees of observable space, it would take approximately 300,000 years of continuous observation time. 300,000 years. Civilization has only existed for a few thousand years. Modern astronomy has only existed for a few centuries. Hubble itself has been in orbit for only 3 decades. You cannot observe the whole universe deeply. The mathematics simply does not work. You must choose. You can look deep, staring at tiny patches of sky for extended periods, seeing the most distant and faint objects. Or you can look wide, surveying large areas quickly, but only detecting bright nearby galaxies. You cannot do both. The universe is too vast, and telescope time is too limited. Telescope time is one of the most precious resources in astronomy. Only a handful of telescopes exist that can see deep into cosmic distance. Hubble, James Webb, the Very Large Telescope in Chile, a few others scattered across the planet. Thousands of astronomers compete for observing time on these instruments. Proposals are submitted, reviewed, ranked by scientific importance. Only a fraction of requested observations actually happen. Every hour of telescope time represents a choice, a decision about what to observe and what to leave unseen. This creates a fundamental trade-off that governs all observational astronomy. Depth versus coverage, sensitivity versus area, detail versus completeness. You can spend weeks observing a single galaxy in exquisite detail, measuring its rotation, its chemical composition, the age of its stars, the presence of a central black hole. Or you can spend that same time surveying thousands of galaxies, cataloguing their positions and rough properties, but learning little about any individual object. Both approaches are valuable, both are necessary, but both leave vast gaps in our knowledge. The detailed observations tell us about specific objects, but provide no sense of how common or rare those objects might be. The wide surveys give us statistics and numbers, but lack the depth to understand what we are actually looking at. We are trying to build a complete picture of the universe by combining these incomplete views, like assembling a jigsaw puzzle when most of the pieces are missing and you are not even sure what the final image should look like. Consider what this means for finding rare or unusual objects. If something exists in only 1 out of every million galaxies, you need to survey at least 1 million galaxies to have a reasonable chance of finding it. But surveying 1 million galaxies deeply enough to detect faint, unusual features might take decades of telescope time. So we compromise. We survey large numbers of galaxies quickly and shallowly, hoping to spot something interesting, and then follow up with detailed observations of the most promising candidates. But this means we miss things. Constantly. Inevitably. Every major telescope has a field of view, a specific area of sky it can observe at one time. Large field of view means you can survey more area quickly, but you sacrifice the ability to see fine details. Small field of view means incredible detail and sensitivity, but you can only observe tiny patches at a time. There is no perfect instrument. Every telescope is a compromise between competing priorities. James Webb Space Telescope, the most powerful observatory ever built, faces the same constraints. It can see farther and fainter than any previous instrument. It observes in infrared wavelengths that reveal the most distant galaxies in the universe. But its field of view is small. To survey even a modest fraction of the sky with Webb would require centuries of observation time. So astronomers carefully select their targets, focusing on the most scientifically valuable regions, knowing that most of the sky will remain unobserved at Webb's sensitivity level. This is not failure. This is reality. The universe is simply too large, too complex, too filled with structure at every scale to observe completely. We are forced to sample, to extrapolate, to build statistical models based on limited data. And every time we do this, we introduce uncertainty. We create blind spots. We miss things that might be fundamentally important, but happen to exist in regions we have not observed. The most frustrating part is knowing that the things we have not seen are not uniformly distributed. The universe is not homogeneous. Structure exists at every scale, from individual stars to galaxy clusters to vast cosmic filaments stretching across hundreds of millions of light years. If we observe only tiny scattered patches, we might completely miss large-scale patterns. We might observe only the densest regions or only the emptiest voids, never realizing that our sample is biased. This is the trap we are caught in. We cannot see everything, so we must guess about what we are missing based on what we have seen. But if what we have seen is not representative, then our guesses will be wrong, and we have no way to know whether our sample is representative until we observe more. But we cannot observe more without centuries of additional telescope time that we do not have. So we stand here, in 2025, with our powerful instruments and sophisticated techniques, having observed less than 0.003% of all galaxies, trying to answer fundamental questions about the nature of reality itself. We are working with incomplete data, biased samples, statistical extrapolations that might or might not reflect the true universe. And the invisible universe simply waits, vast and patient and utterly indifferent to our limitations. So we have established that observing the entire universe is mathematically impossible. Telescope time is limited. The sky is vast. We must choose between depth and coverage, between detail and completeness. But now we need to confront an even more uncomfortable truth. Something that astronomers rarely discuss openly but know intimately. Even when we do detect a galaxy, even when we successfully point our telescopes at it and capture its light, that does not mean we understand it. Detection is not knowledge. Seeing is not comprehending. And the gap between those two states is far larger than most people realize. Let me explain what I mean. When you look at a typical astronomical image, when you see those beautiful pictures of distant galaxies captured by Hubble or James Webb, you are seeing light. Photons that travelled across billions of light years of space, maintaining their journey through expanding cosmic voids, finally arriving at a telescope mirror and being recorded by a detector. That much is simple. That is detection. You have successfully identified that something exists at a particular location in space. But what have you actually learned? What do you know about that galaxy? You know it exists. You know roughly where it is. You can see its shape, whether it is spiral or elliptical or irregular. If you are lucky, and the image is high quality, you can see some internal structure. Maybe spiral arms, maybe bright regions of active star formation. That is useful information, but it barely scratches the surface of what you need to know to actually understand that galaxy. You do not know how far away it is with any precision. You do not know how old it is. You do not know what elements make up its stars. You do not know whether it is moving toward us or away from us or how fast. You do not know its mass. You do not know whether it contains a supermassive black hole. You do not know its star formation rate or its chemical composition or its internal dynamics. You have detected it, but you do not understand it. Understanding requires something more, something far more difficult and time-consuming than simple detection. It requires spectroscopy. Spectroscopy is the technique of splitting light into its component wavelengths. When light passes through a prism or a diffraction grating, it separates into a spectrum, a rainbow of colours each representing a specific wavelength. But the spectrum of a galaxy is not a smooth rainbow. It contains dark lines and bright lines, absorption features and emission features, each one corresponding to a specific chemical element or molecule. These spectral features are like fingerprints. They tell you what the galaxy is made of. But spectroscopy reveals far more than composition. The wavelengths of those spectral lines are shifted by the motion of the galaxy. If a galaxy is moving away from us, its light is stretched to longer wavelengths, shifted toward the red end of the spectrum. This is called redshift. The amount of redshift tells you how fast the galaxy is receding and, because of cosmic expansion, how far away it is. Redshift gives you distance, and distance gives you age. Suddenly you know when that galaxy formed, how long its light has been travelling, what the universe was like when that light began its journey. Spectroscopy reveals the temperature of stars, the speed at which gas is moving inside the galaxy, the presence of elements like oxygen, carbon, nitrogen, silicon, whether stars are young and hot or old and cool, whether the galaxy is actively forming new stars, or whether star formation shut down long ago. All of this information exists encoded in the spectrum, waiting to be extracted and analysed. But here is the problem. Spectroscopy is slow, incredibly, painfully slow. To obtain a spectrum of a faint distant galaxy, you must gather light for hours or even days. You need large telescopes with specialised instruments. You need clear skies and stable atmospheric conditions, and you can only observe one galaxy at a time, or at best a few dozen if you use advanced multi-object spectrographs. The Sloan Digital Sky Survey, one of the most ambitious spectroscopic projects ever undertaken, spent years observing galaxies and obtained spectra for approximately 2 million objects, 2 million galaxies, with detailed spectroscopic data, distance measurements, composition analysis, motion and velocity measurements. That represents decades of work by hundreds of astronomers using dedicated telescopes. 2 million galaxies with spectroscopic data out of 2 trillion that exist. That is 1/10 of 1,000th of all galaxies. For every galaxy we truly understand at a spectroscopic level, 10,000 remain as nothing more than faint smudges of light in an image. Most known galaxies lack spectral data entirely. They appear in surveys as dots, barely resolved points of light with estimated positions and rough brightness measurements. Astronomers can guess their distances based on how faint they appear, a technique called photometric redshift estimation, but these guesses carry enormous uncertainties. A galaxy might be small and nearby or large and distant. Without spectroscopy, you simply cannot tell. This is like seeing city lights from an airplane at night. You know cities exist down there. You can see the glow. You can estimate roughly where the bright spots are located, but you know nothing about those cities. You do not know their populations, their cultures, their histories, whether they are thriving or declining. You see light and you call that observation, but you have learned almost nothing of value. Occasionally, astronomers do land and explore. They select particularly interesting galaxies, objects that seem unusual or important, and invest the time needed for detailed spectroscopy. These become case studies, deep dives into individual objects. A single galaxy might be observed for dozens of hours, its spectrum analysed in exquisite detail, its properties measured with precision. These studies reveal incredible things. They show us how galaxies evolve, how stars form and die, how supermassive black holes influence their surroundings. But these detailed studies are rare, precious, limited to a tiny fraction of galaxies that happen to be bright enough, close enough, or interesting enough to justify the enormous investment of telescope time. For every galaxy studied in detail, millions remain as photometric detections alone. Dots in a catalogue, numbers in a database, detected but not understood. Consider what this means for testing theories about galaxy formation. If you propose a model for how galaxies evolve over cosmic time, you need large samples of galaxies at different distances and ages to test that model. You need hundreds or thousands of galaxies with measured properties. But obtaining spectroscopy for hundreds of galaxies might require years of telescope time. So instead, astronomers use photometric data, which is faster and easier to collect but far less precise. They build models based on incomplete information and acknowledge that uncertainties are large. The situation becomes even worse for very distant galaxies. The most distant galaxies in the universe, the ones that formed in the first billion years after the Big Bang, are incredibly faint. Their light has been travelling for over 13 billion years. It has been stretched by cosmic expansion, shifted from visible wavelengths into the infrared. To obtain spectroscopy of these objects, you need the largest and most sensitive telescopes available. James Webb can do it, but only for a handful of carefully selected targets. Each spectrum might require dozens of hours of observation. We have detected thousands of candidate galaxies at these extreme distances, tiny red dots in deep images. Photometric data suggests they are ancient, formed when the universe was less than 5% of its current age. But spectroscopic confirmation exists for only a small fraction. Most remain candidates, possible early galaxies, detected but not confirmed, seen but not understood. Every astronomical catalogue is filled with objects like this. Galaxies that exist as entries in a database, but about which we know almost nothing. Their coordinates are recorded. Their approximate brightness is measured. Everything else is estimation, extrapolation, educated guessing, based on statistical models derived from the tiny fraction of galaxies we have actually studied in detail. This is the hidden truth behind every claim about galaxy populations and cosmic structure. When astronomers say there are 2 trillion galaxies, they mean we have detected evidence suggesting that number based on tiny samples and statistical extrapolation. When they describe how galaxies form and evolve, they mean we have studied a few thousand in detail and assume the rest behave similarly. When they calculate the odds of finding life on other worlds, they mean we have examined a microscopically tiny sample and are guessing about the rest. Detection gives you awareness that something exists. Understanding requires time, effort, and detailed observation that we rarely have the resources to provide. The universe we have detected is vastly larger than the universe we understand. And that gap, that enormous chasm between seeing and knowing, defines the current state of observational astronomy. We are surrounded by galaxies we have seen but do not comprehend, And the invisible universe, the vast majority we have not even detected yet, remains entirely beyond our reach. We have talked about the limits of telescope time. We have discussed the difference between detecting galaxies and actually understanding them. But now we need to confront something even more fundamental, something built into the fabric of space-time itself. There are galaxies out there, billions upon billions of them, that are not invisible because we have not looked. They are invisible because the universe itself has made them impossible to see with certain types of telescopes. This is not about technology, or time, or resources. This is about physics. The universe is expanding, not just drifting apart, but actively expanding. The space between galaxies is stretching, growing larger with every passing moment. This is not controversial. It is one of the most well-established facts in cosmology, confirmed by decades of observations. But expansion does something strange to light. Something that fundamentally changes what we can and cannot observe. When light travels through expanding space, it gets stretched along with that space. Imagine drawing a wave on a rubber band and then pulling the rubber band apart. The wave gets longer, its wavelength increases. Light behaves the same way. As photons journey across billions of light years of expanding cosmic space, their wavelengths stretch. They shift toward the red end of the electromagnetic spectrum. This phenomenon is called redshift. For nearby galaxies, redshift is minimal. Light shifts only slightly. A galaxy a few million light years away shows barely any redshift at all. Its light looks almost the same as when it was emitted. But as distance increases, redshift becomes dramatic. A galaxy 5 billion light years away has its light stretched significantly. A galaxy 10 billion light years away shows extreme redshift. And galaxies at the edge of the observable universe, whose light has been travelling for over 13 billion years, experience redshift so severe that it completely transforms the nature of their light. Here is what that means in practical terms. Imagine a galaxy forming stars in the early universe, less than 1 billion years after the Big Bang. Those young, hot stars emit most of their light in ultraviolet wavelengths, brilliant, energetic, short wavelength radiation. That light begins its journey across the cosmos, travelling through expanding space. Over billions of years, as the universe grows larger, the wavelengths stretch. Ultraviolet becomes visible blue. Blue becomes green, green becomes red, red becomes infrared. By the time that light reaches Earth 13 billion years later, it is no longer visible at all. The ultraviolet light that left those stars has been stretched into infrared wavelengths. If you point an optical telescope at that galaxy, you will see nothing. Not because the galaxy is too faint, not because your telescope lacks sensitivity, but because the light you are looking for no longer exists in visible wavelengths. It has been redshifted into a part of the spectrum your optical telescope cannot detect. This is why infrared telescopes are absolutely essential for studying distant galaxies. James Webb. Space Telescope observes primarily in infrared wavelengths, specifically because the most distant objects in the universe are invisible to optical telescopes. Their light has been stretched beyond the visible spectrum by cosmic expansion. Without infrared capability, we are blind to entire populations of early galaxies. But even infrared telescopes face limits. As redshift increases, light continues to stretch. Infrared becomes far infrared. Far infrared becomes microwave. Eventually, if distance is great enough, light redshifts completely out of the range of any telescope we can build. There is a horizon beyond which galaxies become fundamentally unobservable, not because they do not exist, but because their light has been stretched into wavelengths we cannot detect. Now, add another problem. Redshift does not just change wavelength, it also reduces energy. Light is composed of photons, individual particles of electromagnetic radiation. Each photon carries energy proportional to its frequency. Higher frequency means more energy. Lower frequency means less energy. When light redshifts, its frequency decreases. Its energy drops. A photon that started as high-energy ultraviolet radiation might arrive at Earth as low-energy infrared. It has lost most of its original energy during the journey. This makes distant galaxies appear incredibly faint. Not only has their light been stretched to different wavelengths, but each individual photon carries less energy than it did when it was emitted. The longer the distance, the more severe this effect becomes. Some extremely distant galaxies deliver only a handful of photons per second to Earth. A few photons. Out of trillions emitted by billions of stars, only a tiny fraction completes the journey across cosmic distances, and each of those photons arrives weakened, redshifted, carrying far less energy than when it began. Detecting such faint signals requires extraordinary sensitivity and extremely long exposure times. This is why the deepest images of the universe require hundreds of hours of observation. Astronomers are literally counting photons. They point the telescope at a patch of sky and wait for those rare photons to arrive, accumulating them one by one, slowly building up enough signal to distinguish a galaxy from random noise. It is an exercise in patience and precision, pushing technology to its absolute limits. But redshift creates another subtle problem that most people never consider. When you observe a distant galaxy, you are not seeing it as it exists today. You are seeing it as it existed billions of years ago when the light you are observing was emitted. A galaxy 10 billion light-years away appears as it was 10 billion years ago. The universe was younger then, smaller, denser. That galaxy has continued evolving since then, forming new stars, perhaps merging with other galaxies, changing in ways you cannot observe because that light has not reached you yet. Now combine this with redshift. The light you see from that distant galaxy is not just old, it is transformed, stretched, shifted into wavelengths that no longer represent what the galaxy was actually emitting. You must correct for redshift to understand what you are really looking at. You must mathematically unstretch the light, calculate what wavelengths it had when it was emitted, figure out what that tells you about the stars and gas and physical processes happening in that galaxy billions of years ago. This is not simple. Redshift corrections require precise measurements. You need spectroscopy to determine exact redshift values. Without that, you are guessing. And remember from the previous discussion, spectroscopy is time-consuming and available for only a tiny fraction of galaxies. Most galaxies in deep images have estimated redshifts based on photometric data, which means their distances carry large uncertainties. You might think you are looking at a galaxy 12 billion light-years away when it is actually 10 billion light-years away. That error changes everything about your interpretation of its properties. Distance and redshift together create a conspiracy of invisibility. Many galaxies are invisible to optical telescopes because their light has redshifted into infrared. Many are invisible to infrared telescopes because they are too faint, their photons too sparse and too low energy to detect. Many exist at distances so great that even the most sensitive instruments struggle to capture enough light to confirm their presence. Physics itself, the expansion of space, and the properties of light creates barriers to observation that technology alone cannot overcome. This is not theoretical. This is happening right now. There are galaxies in the observable universe that we will never see with current technology, not because they are too far away in principle, but because their light has been stretched and weakened to the point of undetectability. They exist in a realm of physical invisibility, present in space-time, but absent from our data. And here is the truly unsettling part. We do not know how many galaxies fall into this category. We do not know what fraction of the universe is invisible to us due to redshift and distance effects alone. We can calculate theoretical limits based on telescope sensitivity and expansion rates, but we cannot observe what we cannot detect. The invisible universe might contain structures, galaxy types, and phenomena that remain completely unknown simply because their light never reaches us with sufficient strength to register. Every deep field image, every survey of distant galaxies, every claim about the early universe is constrained by these physical limits. We see what physics allows us to see. Everything else remains hidden, not by choice or lack of effort, but by the fundamental nature of light traveling through expanding space, and we have no way to know what we are missing until we build more sensitive instruments and look again. The universe fades from view, not because it ends, but because observation itself has limits, and those limits are far more restrictive than anyone wants to admit. So we have established the scope of our ignorance. We see a microscopically tiny fraction of all galaxies. We understand even less. Distance and redshift hide entire populations from our view. Physics itself conspires to keep most of the universe invisible. You might think that what we are missing is simply more of the same. More spiral galaxies, more elliptical galaxies, more of the types we have already catalogued, just in greater numbers scattered across cosmic distances we have not yet surveyed. You would be catastrophically wrong. The invisible universe is not just larger, it is fundamentally different. Every time we push technology forward, every time we observe in new wavelengths or reach greater sensitivity, we discover things that should not exist according to our models. Things our theories never predicted. Structures and objects that force us to rewrite our understanding of how the universe actually works. In 2025, James Webb Space Telescope revealed something extraordinary. Over 1,700 early galaxy groups existing less than 1 billion years after the Big Bang. These are not individual galaxies scattered randomly through space. They are groups, collections of galaxies already clustered together, gravitationally bound, forming the seeds of what would eventually become massive galaxy clusters. Their light has traveled more than 13 billion years to reach us. We are seeing them as they existed when the universe was less than 8% of its current age. This discovery violated expectations. Galaxy formation theory suggested that galaxies formed first as individuals, and only slowly gathered into groups and clusters over billions of years. Large-scale structure was supposed to develop gradually as gravity pulled matter together across cosmic time. But these early groups show that clustering happened far faster than anyone predicted. Galaxies were already organizing themselves into coherent structures within the first billion years of cosmic history. These objects were completely invisible before infrared technology reached sufficient sensitivity. Optical telescopes saw nothing in those regions of sky. The light from these early galaxies had been redshifted so severely that it existed entirely in infrared wavelengths. They were there all along, hidden not by distance alone but by the physics of cosmic expansion. Until we looked in the right wavelengths with sensitive enough instruments, they remained unknown, undetected, missing from every model and theory about early universe structure. But the surprises go deeper. Those early galaxy groups are dominated by small galaxies, not massive bright spirals or giant ellipticals, but small faint dwarf galaxies that would be almost impossible to detect if they were not clustered together. Previous models assumed that large galaxies drove the major events in cosmic history. Large galaxies were supposed to dominate star formation, regulate gas flows, and control the evolution of cosmic structure. These observations suggest the opposite might be true. Small galaxies may have driven cosmic reionization, one of the most important phase transitions in universe history. In the early universe, hydrogen gas was neutral, opaque to most light. Then something happened. Energy from stars and perhaps early black holes ionized that hydrogen, transforming it from neutral atoms into charged particles. The universe became transparent. Light could travel freely across cosmic distances. This transition fundamentally changed the nature of cosmic structure formation. For decades, astronomers assumed large galaxies provided most of that ionizing radiation. But if small galaxies were far more numerous in the early universe than we realized, if they were forming stars at higher rates than our models predicted, then they might have contributed far more to reionization than anyone suspected. This completely overturns earlier assumptions about which objects shaped cosmic evolution during the first billion years. And we only know this because James Webb can see in infrared wavelengths with unprecedented sensitivity. Before Webb, these galaxies were invisible. They existed in our data as voids, empty patches where our optical telescopes saw nothing. We built theories based on incomplete observations, never realizing that entire populations of objects were missing from our samples. This keeps happening, not occasionally, constantly. The history of astronomy is filled with examples of invisible phenomena becoming visible and immediately overturning established understanding. Dark matter was discovered because galaxy rotation curves did not match predictions based on visible matter. Dark energy was discovered because distant supernovae behaved differently than expected. Supermassive black holes were hidden at galaxy centers until X-ray telescopes revealed their presence. In 2024, astronomers discovered something called the Big Ring, a massive structure composed of galaxies and galaxy clusters stretching across 1.3 billion light-years of space. It forms a nearly perfect ring shape when viewed from Earth. This structure is so large it violates the cosmological principle, the assumption that the universe should be roughly uniform at the largest scales. Structures this enormous are not supposed to exist, according to our models of how matter clusters under gravity. But it does exist. We found it by mapping galaxy positions across huge volumes of space, something only possible with large-scale surveys that catalogue millions of galaxies. Before we had that data, before we mapped enough of the universe to see patterns at billion light-year scales, we had no idea such structures were possible. Our theories were built on incomplete data. They worked fine for the small fraction of the universe we had observed. But they failed to predict what we found when we finally looked at larger volumes. This is the fundamental problem. You cannot know what you are missing until you observe it. You cannot test theories against phenomena you have not detected, and if your sample is biased, if you observe only certain types of galaxies or certain regions of space, then your theories will be biased too. They will work for the limited data you have, but fail when confronted with the full reality of what actually exists. None of this is visible to your eyes. None of it appears in the night sky you can see from your backyard. You are blind to the actual structure of reality, living inside a tiny bubble of local space, unaware of the vast architecture surrounding you. This should be humbling. It should make you question every intuitive assumption you have about the universe. Because those intuitions are based on perception, and perception shows you almost nothing. Now consider what this means for our scientific understanding. We have built sophisticated cosmological models. We can calculate the age of the universe to within millions of years. We can describe the formation of the first atoms 380,000 years after the Big Bang. We can map the cosmic microwave background radiation and measure tiny fluctuations that seeded galaxy formation. We can predict the ultimate fate of the cosmos trillions of years in the future as dark energy drives accelerating expansion. All of this impressive theoretical edifice rests on observations of a microscopically tiny fraction of what exists. We have studied perhaps 0.003% of all galaxies in any meaningful detail. We have obtained spectroscopy for 1/10 of 1,000th. Most of the universe remains not just unobserved, but fundamentally invisible to current technology due to distance, redshift, and the limits of detection. This does not mean our models are wrong. It means they are incomplete, built on limited data, constrained by what we have been able to observe rather than by what actually exists. Every time we expand our observational capabilities, we find things that require modifications to theory. Sometimes small adjustments, sometimes complete overhauls of our understanding. The pattern is clear. The invisible universe does not simply confirm our expectations, it challenges them. Think about what this means for the search for life beyond Earth, one of the deepest questions humanity has ever asked. Are we alone? Does life exist elsewhere in the cosmos? We have searched for decades using radio telescopes, looking for signals from intelligent civilizations. We have studied thousands of exoplanets, worlds orbiting other stars, searching for atmospheric signatures that might indicate biological activity. We have found tantalizing hints, but no definitive proof. But we have only checked a tiny fraction of possible locations. If we have catalogued only a few million galaxies out of 2 trillion, then we have surveyed only that same microscopic fraction for potential life-bearing worlds. We have examined perhaps 0.003% of all galaxies for signs of life. 0.003%. For every galaxy we have searched, over 33,000 remain unexamined. The odds of life existing elsewhere are not based on comprehensive surveys. They are based on statistical extrapolation from limited samples. We find that planets are common around stars. We estimate that billions of potentially habitable worlds exist in our galaxy alone. We multiply those numbers across trillions of galaxies and conclude that life must be abundant. But these are educated guesses, not proven facts. We are extrapolating from a tiny visible sample to make claims about an invisible majority we have never observed. Maybe life is far more common than we think, existing in forms and environments we have not yet imagined. Maybe it is far rarer, concentrated in specific types of galaxies, or cosmic neighborhoods we have not yet identified. Maybe it follows patterns only visible when you map billions of galaxies instead of millions. We cannot answer these questions without more data, without observing more of the invisible universe, without expanding our surveys beyond the narrow slice of cosmic space we have examined so far. Now, look forward. What comes next? How do we begin to chip away at this enormous deficit of observation? Future telescopes will help. Projects are planned that will survey larger areas of sky with greater sensitivity. The Vera Rubin Observatory will scan the entire visible sky every few nights, cataloguing billions of galaxies and monitoring how the universe changes over time. The Nancy Grace Roman Space Telescope will survey huge areas in infrared, finding distant galaxies that are invisible to optical instruments. Next-generation ground-based telescopes with mirrors 30 meters across will gather light from the faintest sources. These instruments will dramatically increase our observational coverage. Instead of studying 0.003% of galaxies, we might reach 1 or 2%. That sounds small, but it represents a 100-fold increase in data. And history shows that every order of magnitude increase in observational capability reveals fundamentally new phenomena. The invisible universe will become slightly less invisible. But even these ambitious projects face limits. They cannot observe everything. The universe is simply too vast. Even with decades of observation from multiple instruments, we will still sample only a small fraction of what exists. The invisible universe will remain mostly invisible for the foreseeable future. This is not defeatism. This is mathematical reality. We must accept our limitations while working to expand them. Artificial intelligence and machine learning will accelerate discovery. Algorithms can analyze millions of galaxy images, identifying unusual objects and patterns that human astronomers might miss. Citizen science projects can distribute the work of classification and analysis across thousands of volunteers, each contributing small amounts of time that add up to enormous collective effort. These approaches help us extract more information from existing data while we wait for new telescopes to come online. But ultimately, progress requires observation. We must point our instruments at the sky and collect photons. We must build bigger telescopes, more sensitive detectors, instruments that observe in wavelengths we have not yet thoroughly surveyed. We must invest time and resources and human ingenuity into the patient work of mapping the cosmos one galaxy at a time. Understanding our cosmic ignorance is the first step toward reducing it. Knowing that we have seen almost nothing keeps science humble. It prevents overconfidence. It reminds us that our theories are provisional, subject to revision when new data arrives. It forces us to acknowledge uncertainty and remain open to discoveries that challenge our assumptions. The invisible universe is not unreachable. It is simply unseen. There is no fundamental barrier preventing us from observing it. No law of physics that makes it forever inaccessible. We just need time and technology and persistence. Every year we observe more galaxies. Every decade we build more powerful instruments. Every generation of astronomers pushes the boundaries of observation a little further. The cosmos does not hide from us out of malice. It is simply vast, larger than our instruments, older than our civilizations, more complex than our models, and mostly invisible because we have only just begun to look. You stand on a small planet orbiting an average star in an unremarkable galaxy, looking out at a universe where 200 billion trillion stars exist, and you can see 9,000 of them. Where 2 trillion galaxies exist, and we have studied a few million in any detail. Where most of reality remains unseen, waiting patiently for the day when our technology and curiosity finally catch up to cosmic scale. That day is coming, slowly, incrementally, one observation at a time, and when we finally see what has been invisible, when we map the full architecture of the cosmos and understand the complete diversity of galaxies and structures that exist, we will look back at this moment and realize just how blind we were. The invisible universe is not empty, it is not absent, it is full of wonders we have not yet imagined, structures we have not yet detected, and perhaps life we have not yet found. And it is waiting for us to finally open our eyes and see what has always been there.